Hello guys, welcome back to our channel. Today we are solving a new problem. In this problem, we are given a closed loop control system, which means the system uses feedback to regulate its behavior as stated in examples we solved before. The behavior of such a system is described by its characteristic equation, which is the Laplace function equated to 0. The equation is very important because the roots of the equation determine how the system responds over time. Instead of solving for the roots directly, which can be very time consuming, we use the Ruth-Hurwitz stability criterion. This method provides a systematic way to check whether the system is stable or unstable. Stable or unstable as said by organizing the coefficients into a table. Hence, our main objective is to use this method to analyze the stability of the given system. Thank you.
In a control system, stability refers to how the system behaves over time after it is disturbed or given an input. A system is considered stable if its output eventually settles to a steady value and does not keep increasing or oscillating uncontrollably. This behavior depends on the location of the roots of the characteristic equation in the S-plane. If all the roots have negative real parts, that is, they lie in the left half of the S-plane, then the system is stable. However, if any root has a positive real part, the system becomes unstable, meaning that the output can grow without bound. The Ruth-Hurwitz criterion helps us to determine this by checking for sign changes instead of solving for the roots directly.
So we've been given this equation to use Ruth-Hurwitz criterion to solve. So we first start by writing all the S components on the first column. So write S3, S squared, S and S naught, S1. So then on the next column, that's on the row of S3, we write all the odd coefficients. What I mean by the odd coefficients, we have here to be A1, here to be A2, A3, and A4. So we write all the odd coefficients on the S3 row. So what we do is we write 1 over here because that's the first, and we skip to 3.5. Then on the next one, we write the even for the S2. So that's 4.5 followed by what's 1.5. Then over here, since we don't know the rest of them, we put B not here, we put B1 here, put C not here, we put C1 here. So now it's up to us to find for B not and B1, C not and C1. So to find for this, what we do is that we use a formula where B not is equal to the determinant, that's 1, 3.5, 1.5, and 4.5, all over 4.5. So basically we will get 4.5 multiplying 3.5 minus 1.5 multiplying 1, all divided by what? 4.5, which is going to give us 3.17. So B naught is equal to 3.17. So then how do you find for C naught? How do you find for B1? B1 is equal to 0 because we know the next row, they are all 0, and when they multiply it, they are going to give us 0. But let's try and prove it. B1 is going to give us what? We still maintain the first row, but we still maintain the first column, but the next row is going to be all zeros. So we are going to get what? 1, 4.5, then here will be 0, here will be 0, all over what? All over 4.5, which is going to give us what? 4.5 times 0 minus 0 multiplying 1 all over 1.5, which is equal to 0. So B1 is also equal to 0. Now, how do we find for C naught? To find for C naught, we are going to get C naught to be equal to what? C naught to be equal to what? 4.5 B naught, and the other side 1.5, then B1. All right, but we know the values for B0 and B1 already, so it's going to be simple, all over B0. So it's going to be simple. It's going to give us 4.5 multiplying B1 minus B0 multiplying 1.5 all over B0. Right? Yeah. But we know B0, where B0 is equal to what? 3.17, and B1 is equal to 0. So what are we going to get as our final answer? We're going to get 4.5 multiplying 3.17 all over what? 3.17, which is going to give us this is going to give us 0, and this is going to give us 3.17. So all divided by B0. So that's going to be all divided by, so we're going to get 3.17 multiplying with 1.5. That's going to give us 1.5. Yeah. So I hope you get it. So we are going to get we're going to get 3.17 multiplying 1.5 all over 3.17. That's going to give us 1.5. So we are going to get C naught to be equal to what? 1.5. And how do you find for C1? So C1 too basically is going to be like B naught, which is also equal to 0. So now our final criterion, we have S3 here, we have S2, S1, S0. We are going to get what? 1 and 3.5. We have 4.5. We have 1.5. Then we have B naught, that's 3.17. Then we have 1.5 for C naught. Then we have 0 for this, 0 for that. That's it. Thank you very much.
Alright, so hi, I'll be taking over from where my colleague left off. So after setting up the first two rows, the next step is to calculate the elements in the S1 row, and we do this using the Ruth-Hurwitz formula method, yes, which combines all the values from the initial rows above. Yes, and then after inputting the values, you get approximately 3.17, and this is the value for the element in the S1 row, the first element in the S1 row. Yes, it is important because each new row depends on the values calculated from the previous row. Thank you.
After calculating the S1 row in the previous step, we now move to the final row of the route table, which corresponds to S0. So the value in the S1 row is obtained directly from the last element of the row, which was calculated as 1.5. This happens because we have reached the lowest order of the polynomial, so no further calculation is required. At this stage, the route table is complete. We can now go on further to extract the first column values to analyze the system's stability.
So now the route table is complete. The next step is to focus on the first column, because that's where we determine the stability. So we extract the values of the first column, which are 1, 4.5, 3.17, and then 1.5. These values are very important because that's what the Ruth-Hurwitz Criterion uses to check signs of changes. Yeah. Instead of analyzing the whole thing, we can only use the values for the first column. By observing the numbers carefully, we prepare for the next step, which is to determine any sign changes that occur between the negative values. Then we move to the next step. Thank you.
In this step, you will carefully examine the column values, the first column values, to check for any sign changes from one row to the next. The values you had were 1, 4.5, 3.17, and 1.5. When we compare each of these values, there are no sign changes from positive to negative or negative to positive. And according to the Ruth-Hurwitz Criterion, the number of sign changes corresponds to the number of roots in the right half. Since there are no sign changes, it is a key indicator of stability. Thank you.
Okay, so since all the roots lie in the left half of the S-plane, the system does not exhibit any unstable behavior like unbounded flow. Therefore, the system is completely stable and will produce a bounded and predictable output for any bounded inputs. Therefore, in summary, using the Ruth-Hurwitz criterion allowed us to confirm stability quickly and efficiently without solving the equation explicitly.